Good afternoon. Happy Monday. This is AP Calculus AB. We're going to take a look at problem set, problem number 6. This was a pretty challenging problem on the problem set and required a lot of attention to detail. Now, if I recall correctly, the graph of the original function looked something like this. And I'm going to try to put the original problem in black and then the answer in a different color, actually a couple of different colors. But if I recall correctly, the original problem went something like this. It's increasing and then eases up a little bit and then tops out somewhere. And then does it start going up again?
Yep.
Yep.
Okay. So, it's very common for students to look at this problem, to oversimplify it just a little bit, and to say, let me lock down this part also. It's very common for students to make this mistake. They'll say, well, we got a horizontal tangent line here, horizontal tangent line there, so it looks like we're going to have a parabola that opens either up or down. And since the slopes of the tangent lines are positive over here, we're going to go opens up. And so that's my answer for f prime. If this is f. And then to get f double prime, it said selected answers. So it didn't give you the, on the answer sheet, it didn't give you the answer for f prime, but it did give you f double prime. And going from negative slope to positive slope. So probably a lot of people were hoping that the final answer would look like this, f double prime. Am I right? Is that what you were hoping for? Some of you are saying, yeah, that's what I was hoping for. But that was not the correct answer. Why? What's wrong with that approach? Well, here's what's going on. Let's put the n in vegan tomorrow. I mean, there's no doubt that there's a horizontal tangent line right here. Another horizontal tangent line right there. That part is correct. But now when we try to get the graph of f prime, let's do this numerically. Let's just come up with numeric estimates of the slope. This may be something like 3. That's easing off here. 3, 2, 1, 2, 3, 2, 1, 0. See, it doesn't take a smooth journey from 3 down to 0. It's going like 3, 2, 1, but then do you see how it starts getting steeper again? Shake your head yes or no. Do you see how it starts to get a little bit steeper? So that means that the derivative would have y values that are big. They're coming down 3, 2, 1, 2, then they go up again. And then they finally make their way down and up like that. So I would argue that the graph of the first derivative would have a minimum value that's lined up with this point, which later on in this course, we're going to call these points of inflection, where we're going to call this graph, this portion of the graph concave down, and that part then switches to concave up. Then it does it again. It goes to concave down again. So how can you tell whether a graph is concave up or concave down? This is foreshadowing, not part of the homework, but if you were to draw tangent lines to a graph, when the tangent lines that you draw to a graph camp out above the graph, that's a sign that the graph is concave down. But when the tangent lines, like over here, they're above, right, there's just one section here where it's concave up. This section here, if you were to visualize a tangent line, it's actually hanging out below. I'd like to do an exaggerated point of inflection. Later on in this course, you're going to be held accountable for identifying points of inflection. Notice how over here, the tangent lines camp out above the line, but over here, the tangent lines are camped out below. See that difference? That's an objective indicator that this part of the graph is concave down. It's like part of a bowl of cereal. You know how when you put cereal in your bowl and then you turn the bowl over, the cereal falls out? It's concave down. When the bowl is upside down, that graph would be concave down. But when the bowl is not, like the cereal has not gotten soggy yet and you're not dumping it down the sink, when the bowl is still holding cereal, it's concave up. Well, mathematically, we can describe the difference between these two. If the tangent lines are camping out above, it's concave down. If the tangent lines are camping out below the graph, it's concave up. Anyway, but you didn't have the language of concave up, concave down. All you knew going into this assignment was that the graph of the derivative has y coordinates that come from the slopes of the tangent lines. So here's how you could have actually gotten it, and maybe some of you did. Slopes of the tangent lines, you can come up with numerical estimates, like pretty steep, 3, 2, 1, but then they get steeper again, 2, 3, and then they start coming down again, 2, 1, 0. So if this blue graph is the graph of the first derivative, then switching to green, we've got 3 points, and I don't know exactly where these are, because I don't have the exact one, but we go from negative slopes to positive. So that's why the second derivative looks like roughly this graph. So it's kind of weird because you're going from, and so now it sounds like there's some follow-up questions. Who had a follow-up question on this? Or someone said, how can it be smaller? Is that? Like less x-intercepts?
Right.
Yeah, that's, okay, so the question is, for those of you watching on YouTube, the question is, how can there not be fewer x-intercepts? Keep in mind that usually the number of x-intercepts goes down as the derivative number goes up. So you're observing something pretty important. Usually when you have something like y equals a third degree function, then the function might look something like this. 2 turns, third degree. Not every third degree function has 2 turns, but some of them do. So it's like, okay, 2 turns, and then for y prime, you're expecting there to be just 1 turn. It goes from positive slopes, so it's going like this. That's y prime. And then y double prime has only 1 turn because, look, goes from negative slope to positive, so it looks like that. Y double prime, you could keep going. Y triple prime, the slope of 1 would be a horizontal line. So here's y triple prime. So this goes from third degree to second degree. A polynomial or a parabola is second degree. Straight line has a first degree function. This is a 0 degree function. And then the fourth derivative, the derivative of 0, or the derivative of this horizontal line would be another horizontal line because the slope of a horizontal line is 0. Therefore, the fourth derivative, and we don't do 4 primes, we go to Roman numerals. Fourth derivative would be 0. The fifth derivative would be 0. Yeah, you're right. That's usually a pattern that we see. The reason this one is different is because we have what's called the point of inflection, where the concavity changes from concave down to concave up. It's not easy to see, but the purpose of this problem is just to raise your awareness that you have to have a high level of attention to detail when you're looking at the graph of f and trying to come up with the graph of f prime. And my recommendation to you in the future is to do some numeric estimates. Go along and whisper to yourself numbers that correspond to the slopes of the tangent lines, just like I did. 3, 2, 1, 2, 3, 2, 1, 0, which means the heights of the golf balls go 3, 2, 1, 2, 3, 2, 1, 0. Any follow-up questions on that? Adam, have I answered your question to your satisfaction? Yeah. So yeah, this one was challenging. They're not always that challenging. Okay, so those of you who are ready to turn in problem set problems 6 and 7, do that now. I'm just going to pause the camera here as we take care of turning stuff in. Welcome back. Off-campus learning day had several problems from the textbook, starting with number 43. Number 43, f was given as a line with a slope of 1. Therefore, the derivative, which you saw in the back of the book, should have been the horizontal line y equals 1. Number 44, we had a horizontal line whose slope is 0. That's why the derivative for number 44 should have been the horizontal line y equals 0. Any questions on 43 or 44? All right, 45, f was given as a parabola, therefore your answer should have been a line with positive slope. Notice number 46. 46 is kind of challenging. It turns out that when a graph of a function has a cusp, the tangent line slope is undefined. It's like it teeter-totters back and forth. The tangent line doesn't know what slope to take on. That's why the graph of the derivative on problem 46 is a piecewise function. The slopes of the tangent lines are -1, and then suddenly they switch to +1. So the graph would really have two open circles in it. An open circle at 4, 1 and 4, -1. Golf ball 4's height is undefined because you cannot take the derivative of a function at a point where it has a cusp. You just can't do it. There's no established slope for the tangent line, and therefore we just leave that blank. If they had asked you a different question, like what's the equation for the derivative, you would write a piecewise function. You would say f prime of x is 1 for all x is greater than 4, -1 for all values of x less than 4, and this isn't quite on the camera, I've got to move it over to get it on the camera, and then the first derivative is undefined when x is equal to 4. So, that's kind of tricky. Number 47, the function f was given. It looks like the slopes of the tangent lines are close to 0 but negative, and then they get more and more negative, approaching possibly -infinity or maybe only -4. So it's really not clear from the graph whether we have an odd vertical asymptote at x equals 0, or it could be a jump. Maybe the slopes of the tangent lines are going -1, -2, and then stopping at -3, in which case the derivative would take you down to -3. There is a cusp, so no derivative at x equals 0. Then it suddenly flips to positive slopes. Maybe it's going 3, 2, 1, 0. Maybe it's going infinity, 1 million, 500,000, 10, 5, 9, 8, 7, 6, 5, 4, 3, 2, 1, approaching 0. So you could have either this green graph as a derivative or that one. In the back of the book, do they have a vertical asymptote like this one, or was it more like, it was like this one? Yeah, but it's not clear. It's not clear whether it's this green graph or that green graph. Either one would be acceptable. Jack, did you have a follow-up question? Well, let's store the slope of the tangent line in the y-coordinate of the graph of the derivative. Can you give me some numeric estimates of the slopes of the tangent lines here? Like starting here, that's about what? Maybe -1/10, somewhere around there. Yeah, so that's why on the derivative, I've got like -1/10 for this. Keep going, call out estimates of the slopes. Good. Yeah, so it looks like the y-coordinates on the derivative are -1/10, -1/2, -1, -2, -3. It could be it's going all the way down to infinitely steep, or it could be it's just going down to -3. Can't really tell. Getting derivatives using the graphical approach is an approximation technique at best. You're just trying to approximate it. And then it suddenly flips positive slopes. 1 million, 1,000, 100, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.5, 0.1, 0.0, 1.001, getting closer and closer to 0. Does that answer your question then on what's going on? That was 47. 48 was a semicircle. And it looks like we are going from infinitely positive slope through 0 to infinitely negative slope. So this green graph, I think, would be a good representation of the first derivative. 49 was to come up with an example. There's many. You could come up with an example of a graph whose derivative is always negative. You could do a line with negative slope or any other function that's always decreasing. Here's an example of a slope where there's, I forget how they worded it, but basically you had to have 2 turns in it. Do you have any questions on the book homework that was due today? Yes,
Could you
Crystal.
go over 48 again?
Yeah, let's take a look at 48. So number 48, the graph that was given was a semicircle. And it is true, I mean, suppose it's on a circle, you do have tangent lines whose slope is undefined. Vertical lines have undefined slope. So basically, as x is approaching -2 from the right, the slopes of the tangent lines are approaching -infinity. Well, here up top, the slope of the tangent line is 0. So take a look at what the derivative's value does. It drops from something approaching infinity down to 0, and then it starts going to negative slopes, -1/2, -1, -2, -3, all the way down towards -infinity. The slopes are getting so steep and negative that the graph of the derivative looks like this. So we're okay on that one? All right. So we're putting the G in vegan tomorrow, looking at the derivative concept graphically. Okay? So now, further questions on the homework that was due today? Okay, let's jump into the new material now. If I recall correctly, when we were going through the handout, the most recent handout we had talked about these problems, the algebraic definition of derivative, and this is one of the pages that was on that handout. Some of you have a paper copy of this, others of you were taking notes online. But take this out and open to the page that looks like this and tell me, did we do problem 1 or did we stop the lesson before we got here? Problem 1, did we do it in 7th period? Yes, thumbs up for yes. Okay, so I take it we did not do that one. Did we do a lot of stuff? So yeah, we worked on this one, but that's as far as we went. So let's go now then to problem 1 on this page. Those of you who are in my 4th period class, we already completed problem 1. So since we're in 7th period here making the video, we're just gonna, if you want, you can fast forward the video to get to the point, to the next problem. Okay, so here we go. The directions read, write an equation for f prime of x. Now at this point in the course, we're not using the shortcuts for taking derivatives. The shortcuts for taking derivatives make this into a no work problem. All you do is write the answer. But we're not at that point in the course yet. That's going to be later this week. Later this week, we're going to take the no work approach. Now we're still in the lots of work approach, where whenever they ask you to find an equation for f prime, we need to write the definition of the derivative in limit form. It's the limit as h approaches 0 of f of x plus h minus f of x over h. So I'd like to see if you can pull off the algebra here. I'm going to pause the camera while I tour the room. Using this definition of f, would you please attempt to find f prime of x? So camera's on. All right, let's take a look at this. In case you're wondering, how do you get this first line? Think of every function as having 3 components, an input, a rule, and an output. The input is x. The rule, using the word input, is 1 over input squared. So my question to you is, what is the output of the f function when the input is x plus h? The rule is 1 over input squared. And we use input, so it would be 1 over input squared. There it is, 1 over x plus h squared. Copy down the minus. When the input is x and the rule is 1 over input squared, the output is 1 over x squared. Instead of dividing by h, I'm going to multiply by the reciprocal of h. So you would ask me a question on that one. Does that answer your question about where this came from? I just did 1 over input squared because the rule for the f function is to take 1 divided by input squared. So if the input is x plus h, wouldn't the output be 1 over input squared? Does that make sense? Yeah, okay. So now the hard part, that's the first hard part. The second hard part is getting a common denominator. Multiply by 1 in the form x squared over x squared here. On the second fraction, multiply by 1 in the form x plus h squared over x plus h squared. So I hope your next move was to write the limit as h approaches 0 of x squared minus the quantity x squared plus 2xh plus h squared, which is what you get when you expand x plus h squared. The common denominator, since it is common, I write it down only once. Then don't forget that there's an h in there also. When you distribute the negative sign, x squared minus x squared will collapse to 0, and you'll have the limit as h approaches 0 of negative 2xh minus h squared over the common denominator multiplied by h. Let's pause here. Do you have any questions as to how to make it this far? This also has a lot of attention to detail. When we learn the derivative shortcuts, you won't have to do any of this work. So that'll be a happy day. But you have to know the long way to really appreciate the shortcut. Do you agree that when you factor in h out of the numerator, well, actually, I'd like you to just tell me, what is left inside parentheses when I factor an h out of the numerator? Is there a volunteer who can tell me what remains in parentheses? All right, Jack, you're on. Negative 2x minus h is correct. Now that the numerator is factored and the denominator is factored, I can cancel factors that are in both the numerator and the denominator. And so finally, I can take the limit as h approaches 0, which means I don't have to write limit anymore. All I have to do is write the answer. Now, if you replace all of the h's with zeros and simplify, what do you end up with? I'll take a volunteer on that one also. Take the limit as h approaches 0. What's the answer? The answer, we'll call it f prime of x. Who has it? Yeah, go ahead.
Negative 2 over x.
Yeah, at first you might think it's negative 2x over x to the 4th, but Jack is correct in canceling the x's to get negative 2 over x cubed, which, by the way, is negative 2x to the negative 3. But if you wrote this for the answer, you're in good shape. By the way, those of you who are trying some sort of shortcut, those of you who have already learned the shortcuts, the original problem was x to the negative 2. So it makes sense that the final answer is coefficient times x and then subtract 1 from the exponents, right? Okay. So anyway, but we're not doing the shortcuts. When you learn the shortcut, you can write down the answer with no work. It means you can skip this line, the third line, the fourth line, the fifth line, and the sixth line, and you can skip straight to the seventh line without doing lines 1 through 6. That day is coming quickly. Now, that's number 1, part A. We found the equation for f prime of x. But there's a lot more to number 1 than finding the equation, parts B and C. So I'm going to shrink these. I'm going to get rid of this. Since we've already done part A, and you probably didn't write as big as I wrote because you're not trying to get them to see you on YouTube. So now that we've talked about this, now I'm going to shrink it down, delete this thing, and now let's go to part B. Last call for questions on part A? We're good? Okay, part B says write the equation of the tangent line at the given value of x. By the way, it's often a good idea to eyeball the answer, just like at the beginning of the school year when we had a clock, a disc rotating around a clock. It's a good idea to get a visual on the problem so that you know what to expect. 1 over x squared, by the way, is a graph that has an even vertical asymptote at x equals 0. and a horizontal asymptote of y equals 0. That is the graph of 1 over x squared. So when they say, what's the equation of the tangent line at the given value of x? Well, x equals 4, that would be 1, 2, 3, 4. Here's golf ball 4. It looks like they're asking for the equation of the blue line. By the way, what is the slope of the blue tangent line? Is it a positive number or a negative number? It is a negative number. So let's keep that in mind as we use the derivative. When they ask you to find the equation of a tangent line, the best thing to do, part B, is to start with point slope form and then end in point slope form. That's the recommended form for equations of lines in all of calculus. Point slope form is the form where it's least likely for students to make a silly mistake. So here we go. I need a point and a slope. The slope of the blue line is going to be f prime of 4. Why? Because that's what derivatives do. They take x's and they produce as an output the slope of the tangent line. And using our answer from part A, negative 2 over 64, which reduces to negative 1 over 32, you are right. It is negative. It's a negative slope. Happens to be that the slope of that tangent line is negative 1 over 32. We also need a point. The point is 4 comma something. Any ideas to how I could find the y coordinate of the point of tangency, Shriana? What? I'm sorry?
I was going to say just plug 4 into the original equation.
That is exactly what you do. So when you plug 4 into the original equation, what do you get for the height of golf ball 4? 1/16 is correct. It's 1 over 4 squared. So final answer in part B is y minus 1/16 equals negative 1 over 32 times x minus 4. Nothing more, nothing less. Just leave your answer for the equation of the tangent line in point slope form. Remember, your AP test, it's only about 4 hours long, between 3 and 4 hours long, and it's one test that summarizes everything you have for the whole year. So you want to minimize your chance of making mistakes. So that's why you don't want to solve it for y. Don't distribute the negative 1 over 32. Just leave your answer in point slope form, unless you like absolutely have to do. Yes, Adam. Further questions? Part C says solve for x, for all the x values such that the slope of the tangent line is 1/10. Well, let's eyeball that one. Where would there be a tangent line whose slope is 1/10? Would it be on the quadrant 2 portion or the quadrant 1 portion? Class, quadrant 2 portion might possibly have a slope of 1/10, or quadrant 1. Yeah, it looks like all the slopes of the tangent lines in quadrant 1, the quadrant 1 portion, are negative. So if we're looking for a value of x where the slope is 1/10, it would have to be somewhere here in quadrant 2. In fact, you can even eyeball it. We're thinking the answer is probably going to be something like -5, -6, somewhere in there. So what you do for part C to solve this is you interpret the problem as solving for x such that f prime of x is 1/10. That's your starting point. We want to solve for x such that f prime is 1/10. F prime was found in part A to be -2 over x cubed. Solving this equation for x is not too bad using a cross multiply approach. X cubed equals -20. So the cube root of -20 is the exact answer. If someone wanted to know approximately what is that number, you can go to your graphing calculator and find the cube root of -20 by taking parentheses -20 and raising it to the 1/3 power. We're expecting a negative number. It is true. It's about -2.7. So it's plausible that at -2.7, -1, that the slope of the tangent line is 1/10. Any questions on how to get either the exact answer of cube root -20? The standard in calculus is 3 decimals. So if you want to do approximately -2.714, you could do that, -2.714. Both answers will be full credit, provided you attend to precision. Wavy equals here. non-wavy equals there. Question?
I have a question on part B. So how did you get negative 1 over 32 again?
Negative 1 over 32 is f prime of 4. You see, point slope form is calling for the slope. The slope of a line, slope of a tangent line, that would be the output of the first derivative when the input is 4. So that answer we got in part A is really, it's the formula that gives us the slope that we need for part B.
Oh, okay.
Okay? Further questions? All right. Number 2 is a practice problem, but for the sake of time, I mean, it'd be nice to practice. But let's just go to the last page of the handout, which is differentiability. We kind of talked through these sketches, so skip forward all the way to this last page. It should look something like this. Differentiability is a 7-syllable word. Differentiability. Not every day you get to say a 7-syllable word. At least for me, it's not every day. Maybe it is for you every day. But let's practice saying, when I say go, I'd like all of you to say out loud and in unison, differentiability. Ready? Go.
Differentiability.
That's pretty good. Now let's find out what differentiability is. Differentiability is the ability to take a derivative. And I'll just tell you right up front, there's 3 times when you do not have differentiability. 3 graphical clues that a function is not differentiable. 1, if you have a cusp. Just you don't know where to put the tangent line at the cusp. So this function is not differentiable at the cusp. 2, a vertical tangent line. And by the way, vertical tangent lines can be seen with the help of a calculator. Go ahead and take out your calculator and set up the viewing window from -5 to 5 on the x-axis and from -3 to 3 on the y-axis. Now, I would like to demonstrate that the function, I'll just write this up on top, y equals the cube root of x. This is a parent graph that we look at. It's one of your 50 parent sketches. And we look at this in Algebra 2. But the graph looks something like this. And I would like to argue that the slopes of the tangent lines are like 1/10, 1/5, 1, 2, 3, 4, and they actually go up to infinity. This gets so steep it goes up to infinity, then it comes back down to close to 0. To show that, I would like to demonstrate for you how it is the calculator can get graphs of derivatives. Would you, just to show you how powerful the calculator is, go down to y3. If you don't have anything in y3, or yeah, if you do have something in y3, clear it out. I mean, we could put in y1, y2, but I want to show you what happens if y1 and y2 are filled and you want to use y3. Let's type in the cube root function, which is, it can be written as x caret 1 divided by 3. And oops, I forgot the parentheses there. Let's make it x caret parentheses 1 divided by 3. Now, ladies and gentlemen, the derivative is going to look different depending on which mode you're in. Just for now, you don't have to leave it in classic mode, but would you please press mode and go out of math print for now. You can go back in later. But put the cursor on classic and then press enter. So that way everyone has the same rendering on the y equals screen of this derivative idea. So we have, okay, so we put our function in y3. It's the cube root function. I'd like to prove to you that the derivative graph can be obtained on the calculator. Check this out. Press the math, well, with your cursor to the right of the equal sign in y4, with your cursor right there, press the math button. And notice that item 8 on the math menu is nderiv, which stands for numeric derivative. Item 8. Now, the numeric derivative command requires 3 arguments, or 3 inputs. The first of which is the function. Which function? Well, we're going to use y3. We want to take the derivative of this one. So to get y3 in here, we're going to go to vars. So vars is right here. right arrow to the Y-vars submenu and pick up item 1, notice that Y3 is item 3. We're going to sketch a graph of the derivative of function Y3, or if it was typed up here in Y1, you would do Y1, wherever it is, whatever you want the derivative of, put it there. The comma is above the 7, so comma x. We're taking the derivative with respect to x. So for now, trust me on that you need an x. And now, where do we want to take the derivative? For every golf ball, for just one golf? No, we want every golf ball. So it's y3 comma x comma x. This is going to give us the graph of the derivative in purple. And so notice the slopes of the tangent lines are like 1/10, 2/10, 1/2, and they get steeper and steeper. They actually go all the way up to infinity. So there's actually a vertical tangent line on the cube root function, and the calculator gives you evidence that that's really true. And you could push back. You can say, how do I know it's going up to infinity, Mr. Royce? How do I know it's not just going up to 100 or 150 and then stopping? It's not. I mean, we can prove that later, but this is evidence that that we have a vertical tangent line. So same thing here. There's a tangent line that actually goes vertical. Therefore, the function is not differentiable at a vertical tangent line. Also, if we have any discontinuity, we cannot take the derivative. Discontinuity, for example, a jump, a hole, an endpoint, a vertical asymptote. All of those will make it so that we cannot take a derivative. So here we go. The official definition of differentiability is that f is differentiable at x equals c if and only if f is continuous at x equals c. So we need continuity. But clearly we need more than continuity, because here at this cusp, the function is continuous. But we don't have differentiability. So we need another condition. And the condition is this. The limit as h approaches 0 of the derivative, that should be from the left. And sorry about that. I was rushing, so I made a mistake. It's not approaches 0, it's approaches c. So that's my fault. Let's try this again. The limit as x approaches, I had h approaches 0, but I should have written x approaches c from the left of f of x, and make that f prime. So the limit of the derivative from the left has to equal the limit as x approaches c from the right of the derivative. And that's where we're going to pick it up tomorrow. There is no homework due tomorrow, so you can take the night off for period 7. Period 4, it's a slightly different story. Period 4, you'll be fine. So have a good night. We'll see you tomorrow.